All right, class, welcome to lecture number 3 on radiation quantities and units. So, why are radiation measurements important? As mentioned yesterday in class, this would be Clarence Madison Daly, who worked for Thomas Edison. Here, let me just change this. Clarence Madison Daly, here he was about 39 years old, worked for Thomas Edison here. Again, he died from radiation exposure at the age of 39. At that point, Edison decided that radiation wasn't going to be what he would study after that point. This here is Madame Curie. Of course, she worked with radioactive isotopes, responsible for like making portable machines and just giving us a lot of information about radiation. Her body and her like notebook are still radioactive today. We're just waiting for the half-life to reduce at after every century for her. As you can see here, Mary Curie's century-old notebooks are still radioactive, so they're kept in a lead-lined box for protection against radiation exposure. Her body is also highly contaminated, so was placed in a coffin lined with an inch of lead when she was buried at the Pantheon Mausoleum in Paris. So there's her notebook that's radioactive, and her corpse is still radioactive today. With great biological damage comes great responsibility. X-ray related biological damage was reported as early as 1896. Cancer deaths from X-ray exposure were reported as early as 1910. Radiation workers developed reddening of the skin called radiodermatitis due to occupation exposure. Once it was known that the effects of X-rays could potentially cause great harm to the body, somatic damage, methods for reducing radiation exposure started to be investigated. To adequately do so, a method to measure radiation exposure needed to be found. So these are basically examples, pictures of lesions of the fingers induced by ionizing radiation. Skin erythema dose. From 1900 to 1930, skin erythema dose was the method defined as the received quantity of radiation that causes diffuse redness over an area of skin after exposure to radiation. This is a basic and inaccurate way to measure radiation exposure because of the amount of radiation required to cause erythema varied from one person to another. This was not uniform. Since this measurement was so crude, scientists continued to search for a more reliable unit. The new unit needed to be based on exact measurement effects of radiation. Of course, here we can see that the skin is barely red in for number 200. 250 was just barely a little bit of red. 300 was a lot more red. This doesn't work if there's any pigmentation in the skin. So Asian skin, Spanish skin, African American skin would be a lot darker. So this skin erythema dose wasn't a reliable unit of measurement. So they decided to go with the Rankine after the founder of X-ray. The International Commission of Radiation Units and Measurements, the ICRU, was formed in 1925. In 1928, the Second International Congress on Radiology was held. By this time, the Rankine was accepted as the unit of exposure but not clearly defined. The ICRU was given the task of defining this unit of exposure. The International Commission on Radiologic Protection was also established. So the ICRP. It's good to remember this term here because we will talk more about the ICRP, the International Commission, and then we'll talk about the National Commission that we use here in the United States. Tolerance dose, also can be called threshold dose, is a term used for dose occupational exposure persons could be subjected without any apparent harmful acute effects. Acute being short term. Simply put, a dose of radiation lower than which someone has a chance of receiving biological damage. The measured quantity is called exposure, with the Rankine being the unit of measurement. Threshold and tolerance dose are no longer used today. Threshold and tolerance dose are no longer used today, but we will be discussing the term threshold and non-threshold for the rest of the semester. Maximum permissible dose. Early 1950s, maximum permissible dose replaces the tolerance dose. indicates the largest dose of ionizing radiation that an occupationally exposed person was permitted, and that was not anticipated to result in major adverse biological effects as a consequence of radiation exposure. So basically, the dose permitted that would not result in any biological effects was expressed in REM, radiation equivalent man, the unit used for radiation protection purposes at the time, or dose equivalent. We actually still use REM on our Landauer reports that you guys sign every quarter. On radiation protection, tolerance dose, maximum permissible dose not accepted. The idea that no amount of radiation was safe is adopted today. If no amount of radiation was safe and it was impossible to design a work environment where the dose was zero and still be able to perform procedures such as interventional angiography, then what would determine the maximum allowable occupational exposure? The solution was to compare rates of death and accident among various occupations. Some occupations are very hazardous, deep sea diving, professional rock climbing, and others are non-hazardous, trade, government, desk work. In these non-hazardous occupations, there's still a small risk of death or serious injury, 1 in 10,000 about. Radiographers would be considered to these industries that are generally considered safe. So X-ray techs are considered a non-hazardous occupation. Expansion of dosimetry and risk analysis. By the 1970s, radiation units were developed that contained factors that accounted for the effects from different types of radiation: alpha, beta, gamma, X-ray, and neutrons. In 1991, the ICRP, the International Council of Radiation Protection, revised tissue weighting factors. Basically, certain tissues were more radiosensitive. They also adopted the term effective dose. So certain tissues being more radiosensitive, like the gonads, are more radiosensitive than the thyroid. And the thyroid is more sensitive than the skin or the outer bone cortex. Effective dose, the ionizing radiation dose that is deposited in biological tissue. It takes into account the type of radiation, again, X-ray, gamma, neutron, alpha, beta, and the variable sensitivity of the tissues exposed to radiation. So we're not talking about the entire body, we're talking about specific portions of the body. Effective dose is expressed in sieverts or millisieverts. Radiation quantities and units in use today. So very important table, table 4.6, summary of radiation quantities and units. We look here at the type of radiation, X-ray or gamma radiation. The quantity is exposure with an X. The SI unit, which is the international units, are measured in coulombs per kilogram. The medium that it's measured is air. Radiation effective measured is ionization of air. So exposure and air kerma are basically synonymous. The exposure is pretty much replaced with this new term called air kerma. This is measured in grays. There is a gray subscript A here, so that stands for air. The type of radiation on the next part of the column is all ionizing radiations. The absorbed dose is with a D. Again, air kerma. Both are in gray, but in this case, here there's a small subscript of T, so that's for gray tissue. Here it's gray air, here it's gray tissue, and this could be for any object. So it could be a person, it could also be like a banana or in the ground. Amount of energy per unit mass absorbed by object. The type of radiation, all ionizing radiations. Equivalent dose, EQD, sieverts or millisieverts, body tissue, and anything with body tissue, you're going to have a biologic effect. All in ionizing radiations, effective dose, EFD, sievert or millisievert. Again, body tissue, biological effects. Could be something acute, like a skin erythema, or it could be something more like chronic, like cancer or genetic effects. Again, a super important chart right here. So spend a lot of time understanding the quantity, the SI units, what it's measuring. Traditional units are what's used here in the United States. Radiation quantity, we're talking about exposure again. Absorbed dose, this is basically just referring back to the previous slide. Equivalent dose, EQD. Effective dose, EFD. Radioactivity, this is more for nuclear medicine. So this would have to do with Curie, after the person who founded it. The unit of measure in the United States is rem, rad, and Rankins. So again, exposure is Rankins, absorbed dose is rad, equivalent dose is rem, effective dose is rem, radioactivity is Curie. On the next slide after this one, we're going to talk about the SI units, but basically we're talking about the same thing: exposure, absorbed dose, equivalent dose, effective dose, and radioactivity, but in the SI units or the international units. So again, exposure is now in coulombs per kilogram. Air Kerma is in gray. Absorbed dose is in centigrade or milligrays. Equivalent is in sieverts. Effective dose is in sieverts. Radioactivity is in becquerels. International System of Units. SI units are adopted in 1980 and today are the primary units used to define exposure. The traditional units such as the Rankine, which was once the internationally accepted unit for measurement of exposure, now have begun to become obsolete. Other examples include sieverts replacing rem for radiation protection purposes. Even though the traditional units are being phased out, it is still being used in some places as well as on the registry. So we must be able to identify each unit and what measurement it corresponds to. We must also know how to convert between SI and traditional units. Again, I introduced this slide last semester. This is exposure. So when we're looking at it, simply put radiation, ionization, and air. This radiation quantity expressed the concentration of radiation delivered to a specific area. In radiography departments, this value is not easily obtained. It needs a free air ionization chamber pictured here on the right. It's measured in coulombs per kilogram for SI and Rankins for traditional. Again, depending on which machine that you're using you'll see it in coulombs per kilogram. You may see it in SI units, and you may see it in Rankine, the traditional units. The number of Rankins is 2.58 times 10 to the negative fourth to be converted to coulombs per kilogram. If you need to convert from coulombs to kilograms to Rankins, it's the same thing, but you just divide by 2.58 times 10 to the negative 4. We use this measurement for X-ray equipment calibration because the output of an X-ray machine is measured directly with an ionization chamber. So here is the ionization chamber pictured. It's usually right below the X-ray tube. Usually a physicist will attach this to the table. It's a very small device. You get lead diaphragm, X-ray beam, and the ionization of the X-rays can be measured right here with an electrometer. So ionization chamber is attached to an electrometer. Exposure is also called air Kerma nowadays. It replaced the radiation quantity of exposure, calculation of radiation intensity in air. Quantity that expresses radiation concentration transferred to a patient. Like exposure, must be measured using a free air ionization chamber pictured in the previous slide. Acronyms for air Kerma are kinetic energy released in air, kinetic energy released in material, kinetic energy released per unit mass. In a similar way, tissue Kerma can be used to describe the kinetic energy released to a unit of tissue. It may be stated in grays. When the gray is used to indicate kinetic radiation energy deposited or absorbed in a mass of air, it is written as a gray subscript A. When the gray is used to indicate kinetic radiation energy deposited or absorbed in a mass of tissue, it is written as gray subscript T. Air Kerma and fluoroscopy. Air Kerma is the primary concept in fluoroscopic situations since we are concerned with the exposure and the patient's entrance dose. Modern fluoroscopy units have an ability to determine the amount of energy delivered to the patient by the X-ray beam. Referred to as a dose area product, the measurement of radiation energy that is directed into a portion of the patient's body surface. So dose area product we usually see in fluoroscopy. We'll see it on the X-ray C-arm in surgery, and we also see it in CAT scan CT. It could be called DAP, dose area product, or maybe called DLP. DAP usually specified in the unit milligrays per centimeter squared. That's important to remember. This is the amount of air current dose expressed in gray multiplied by the irradiated surface area. So again, our dose is going to be in gray, and then when we talk about a unit of area, that's going to be done in centimeters squared. So milligrays by centimeter squared. Absorbed dose, amount of energy per unit mass absorbed by an irradiated object, responsible for any biologic damage as a result for exposure. This dose is used to indicate the amount of ionizing radiation a patient received during a imaging procedure. So absorbed dose is for the patient, or it could be object as well. The amount of energy absorbed by a structure depends on the atomic number of the tissue comprising the structure. Higher the atomic number, the more absorption occurs. So for instance, when you're talking about bone, bone has an atomic number of 13.8. Air and soft tissue have an atomic number of like 7.4 and 7.6. Mass density of the tissue, higher the density, the more absorption occurs. So the thicker the body part, the more absorption will happen. Energy of the incident photon, the lower the energy, the more absorption occurs. So low kV, you might have more absorption. When you have like mammography that's like low kVp, you're going to have more absorption. The SI unit for absorbed dose is the gray, so it's important to remember what the specific unit of measurement is for each item. So absorbed dose will be gray. The traditional unit is the radiation absorbed dose, the rad. 1 gray is equal to 100 rad. Equivalents of radiation produce damage from different sources of ionizing radiation. Research found that different types of radiation produce different amounts of biologic damage in tissue. Quality factors Q are adjustment multipliers that are used to calculate dose equivalents when different types of ionizing radiation is used. So in this example, 1 gray of absorbed dose of fast neutrons resulted in lab rat death. 1 gray of absorbed dose of X-rays did not kill a lab rat. Radiation producing damage and linear energy transfer, LET. Linear energy transfer, LET, is the amount of energy transferred on average by incident radiation to an object. LET helps explain the need for a modifying quality factor. Radiation with high LET transfers a large amount of energy into a small area and therefore can do more biological damage than radiation with a low LET. X-ray and gamma are considered low LET, like alpha and beta are considered like high LET. Types of ionizing radiation, X-ray photons, the quality factor is 1. Beta particles, quality factor is 1. Gamma photons, quality factor 1. Thermal neutrons, 5. Fast neutrons, 20. High energy external protons, 1. And when we talk about protons and neutrons, sometimes in the body, the protons and neutrons, they collide and they actually stick together, and that actually forms a deuteron. Low energy internal protons is a quality factor of 20. Alpha particles have a quality factor of 20. Multiple charged particles of unknown energy also have a quality factor of 20. So again, these are mostly internal, ingested, inhaled, absorbed inside the body, so they have a higher quality factor. Whereas these are usually outside the body, X-ray photons. As time passes, quality factors were replaced with radiation weighting factors. But if you notice, the numbers are very similar. Equivalent dose. Equivalent dose, EQD, is the product of the average absorbed dose in tissue and the associated radiation weighting factor, WR. The radiation weighting factors takes into account that some radiation are more biologically efficient in causing damage than others. Radiation weighting factors are based on quality factors and LET. For the most part, the radiation weighting factor actually has the same numeric value as the quality factors that were previously used for determining dose equivalence. So again, the radiation weighting factors replace the quality factors. Equivalent dose calculation. Equivalent dose is used for radiation protection purposes. Equivalent dose EQD may be determined and expressed in the SI units of sieverts or millisieverts. EQD equals dose, absorbed dose, times the radiation weighting factor. SV is the unit of equivalent dose equals gray, the unit of absorbed dose, multiplied by the radiation weighting factor. In diagnostic radiology radiation, doses are small that the unit used may be specified in terms of millisieverts. So again, sieverts or millisieverts. So again, the radiation weighting factors replace the quality factors for different types of ionizing radiation, but they're very similar. So X-ray and gamma ray is just 1. Neutrons below 10 kilo electron volts is 5. 10 kilo electron volts to 100 kilo electron volts is 100. 100 kilo electron volts to 200 milli electron volts is 20, and so forth, all the way down. So basically, very similar to the quality factors that were used prior. Alpha particles, again, being 20. Those are the ones that are usually inside the body. Again, when we talk about protons, sometimes they collide with neutrons and form this item called a deuteron, and I would remember that as well. Effective dose. Effective dose EFD provides a measure of overall risk of exposure to humans from ionizing radiation. The NCRP, the National Radiation Council, report number 116 defines effective dose as the sum of weighted equivalent doses for all irradiated tissues or organs. EFD, effective dose, incorporates both the type of radiation, alpha, beta, gamma, used and the radiosensitivity of organ or body part irradiated. The weighting factor that takes into account each specific organ and tissue is called the tissue weighting factor. So before we talked about the radiation weighting factor, and now we're going to talk about the tissue weighting factor. Again, the effective dose has to do more with the type of radiation, and it also has to do with the type of tissue. So it takes both into consideration. The effective dose is the best form of measurement. Tissue weighting factor. More specifically, the tissue weighting factor is a measure for the relative risk in relation to the irradiation of different types of body tissues. This factor is to account for the cancer-form sensitivity of each organ. As shown, gonads have a weighting tissue factor of 0.20, making it the most radiosensitive tissue organ. So here you can look at our list. Gonads are the most radiosensitive, followed by inside the bone, the red bone marrow, which, if that gets irradiated, it can cause leukemia. The colon has epithelial cells in the small bowel mainly, the lungs, the stomach, the bladder, all the way down to the thyroid, which is 0.05. Skin is only 0.01 tissue weighting factor. The outside of the bone surface, has a tissue weighting factor of 0.01, and everything else is 0.05. So again, the most radiosensitive is the tissue weighting factor of gonads at 0.20, and I would remember that one too. Effective dose calculation. To determine effective dose, the following equation is used. Effective dose equals dose multiplied by the radiation weighting factor multiplied by the weight of the tissue. When an absorbed dose D is multiplied by radiation weighting factor WR to obtain the equivalent dose. From that point, the product is again multiplied by tissue weighting factor WT. EFD effective dose is expressed in sieverts or millisieverts. Again, SI units. Collective effective dose. Collective effective dose, COLEFD, is used to describe radiation exposure of a population or group from low doses of different sources of ionizing radiation. Determined as a product of the average EFD effective dose and the number of people exposed. Collective effective dose equals effective dose, average of effective dose of an individual belonging to a group exposed, multiplied by the number of people. So this is measured in person sieverts. So that's the radiation unit for this quantity. Again, we're talking about the collective of individuals multiplied by the number of people. So you have to have person sieverts in as the unit of measurement. If you do the formula and you just write the word sieverts at the end, that's incorrect. I will have you calculate this on an exam. So make sure you understand how to multiply and get the collective effective dose, and you have to have the correct unit of measurement. If you put if you do the multiplication right, and you put in person sievert, then that would be the correct answer. If you do the correct calculation, but you forget to put person sievert in there, the answer is wrong. Box 4.2, determining collective effective dose using the radiation unit person sievert. So this is an example of the previous slide. If 200 people received an average effective dose of 0.25 sieverts, the collective effective dose, COLEFD, is 200 multiplied by 0.25 sieverts equals 50 person sieverts. Total effective dose equivalent, TEDE, defined by the Nuclear Regulatory Commission as a radiation dose quantity used to monitor and control exposure to ionizing radiation. Sum of effective dose equivalent from external radiation exposures and a quantity called committed effective dose equivalent, CED, from internal exposures. So this is in nuclear medicine again when they ask you to swallow a gamma seed or they inject nuclear material into your IV or you have to inhale like a radioactive isotope gas. Takes into account all possible sources of radiation exposure useful in dose monitoring nuclear medicine technologists and interventional radiologist technologists. Traditionally, for occupational exposure, personnel, the whole body TED regulatory limit is 0.05 sieverts. If you want to convert that, it's like 50 millisieverts or 5 rem, the traditional units, and 0.001 sieverts or 1 millisievert or 0.1 rem, the traditional unit for the general public. We'll talk about all the effective recommended limits for the general public, occupation, for pregnant workers, for students, in another lecture as well. Genetically significant dose, GSD, dose to the reproductive organs that would be expected to bring genetic injury to the total population. GSD suggests that gonadal radiation becomes less significant when averaged over an entire population versus just a few of its members. GSD takes into consideration that some people receive more radiation to their reproductive organs than others. This dose is the average annual gonadal equivalent dose of those who are childbearing age. Estimated genetically significant dose GSD for the population of the United States is 0.20 millisieverts, or the traditional units, again, is 20 millirems. Genetic doubling dose, GDD, the radiation dose that produces twice the frequency of mutations that would have otherwise occurred naturally. All right, some important checkpoint slides for you to remember. Conversion for SI units from sieverts to centisieverts is the fraction is 1 times 100 or -2 millisieverts, 1 of 1,000th. Micro is 1 of 1 million, 10 to the -6. Can be applied to any SI units. So again, it's just moving the decimal points over. Conversion of SI units to traditional SI values of dose are 1 to 100 of the older traditional units. Simply put, 1 gray is equal to 100 rad of the traditional, 1 SI unit, the sievert, is equal to 100 rem. So basically like 1 French guy or the SI unit is equal to 100 Statue of Liberties. In diagnostic radiology, 1 Rankine equals 1 rad equals 1 rem, and that's important to remember. Dose unit memorizing chart. So put all your A's together. For traditional units, your absorbed dose is equal to your rads, is equal to your grays, is equal to your patient. Your equivalent dose, your effective dose, is going to be your REMs, your sieverts, your employees, or your techs.